Today we're looking at the start of chapter 6, which is going to deal with special segments within triangles and special parts of triangles. We're going to start out by looking at a couple different things that go on when we have a perpendicular bisector of a side of a triangle. Now, to start with, we know what a perpendicular bisector is. We know that a perpendicular bisector is a line, ray, segment, something that splits a segment, a given segment. In this case, the segment is AB, and my bisector is line C here, or line PC, excuse me, and it splits AB evenly into two spots, so P is the midpoint of AB, and it is perpendicular to segment AB. So that's the name perpendicular bisector. Now, when we look at a perpendicular bisector, the perpendicular bisector theorem tells us that if a point lies on the perpendicular bisector of a segment, it is equidistant from the endpoints of the segment. So big word there, equidistant. And yes, you've got the little meme down in the corner with David Tennant as the doctor. Equidistant, so grown up. If you haven't seen the 50th anniversary special, you'll get you won't get the reference, but it's in there. So big word, equidistant. So any point C, anywhere on that line, anywhere on that purple highlighted line, no matter where I put C on the purple highlighted line, the distance C to B and C to A, those two distances are congruent. In other words, it's forming an isosceles triangle. ACB is an isosceles triangle for any point on there. AC is always congruent to CB. The converse of the theorem says that if a point is equidistant from the endpoints, then it must therefore be on the perpendicular bisector. So essentially, we could write them both together as a biconditional that we learned about back in chapter 2. We could say a point lies on the perpendicular bisector if and only if it is equidistant from the endpoints of the segment. But it's kind of nice to have it as two separate things. Bottom line is, if it's equidistant, it's on the perpendicular bisector and vice versa. So, find each measure. Obviously, these are kind of some worked out examples for us, but if SQ is the perpendicular bisector, that means every point on S, no matter where I put it, is always equidistant from R and P. So if S was where I'm drawing it here, if that's where S was, those two distances would be congruent. So because that fact is true, pretty simply, since this is 6.8, this must also be 6.8. That uses the perpendicular bisector theorem. The second one proved that it is the perpendicular bisector. Well, if H, since H is equidistant from E and G, and it is perpendicular, this must be on the perpendicular bisector, which means EF also has to be 9.5. We have congruent triangles, all sorts of things going on here. It's very quick once we have those two distances the same, and this is a right angle. We have a very quick hypotenuse leg congruent triangles situation. And that is working with our congruent triangles. But the big thing here is getting the measurements down. Pretty simple. And you will notice that excuse me for a second, you will notice that what they really wanted was the length of EG, and that's really just a matter of adding those two up, 9.5 plus 9.5. Again, another worked out example for us, find the length of AD. And again, it's just a matter of using the facts. What do we know? What's the relationship going to be between these two lengths? Are they going to add up to something? Are they equal to each other? What's going on? Well, since that is a perpendicular bisector, we know it's perpendicular from the right angle symbol. We know it's a bisector from the tick marks giving me the congruence. That means these two must be congruent. We set up and solve for x. X is 7. But that's not what the question's asking. The question is asking what's the length of AC. AD. And AD is 5x or 5 times 7, which is 35. So again, we just kind of work through our problem, use a relationship, set up and solve an equation. We've done that many times. Is there enough information from the diagram to conclude that point N lies on the perpendicular bisector of Kn? Okay, do we have enough information in this given diagram? Well, we do know what? We have points K, L, and M are collinear, and N down here forms a triangle. I know KL is congruent to LM by these marks right here. They're yellow, so I'm anti-highlighting them by doing them in black. So we know it's at the midpoint. We know L is the midpoint, but do we know that it is perpendicular? Do we have enough information to conclude that this is a right angle? That's the question. And the answer here is no, I do not have enough information. If I knew that NK is congruent to NM, then yes, I'd be good to go. Because, again, if it's equidistant from the sides, it must be on the perpendicular, or from the endpoints, it must be on the perpendicular bisector. We don't know that. We don't know that's the right angle, so the answer would be no, I don't know it's on the perpendicular bisector. I know LN is a bisector. It is a bisector. I just don't know whether or not it's perpendicular. So use a diagram and the given information to find the indicated measure. Zx is a perpendicular bisector of Wy. So we're given it's a perpendicular bisector, which means I know that these two are congruent. And that means that these two have to be congruent. That's what it means it's a perpendicular bisector. YZ is 13.75. Find WZ, obviously, must also be 13.75. Once again, ZX is the perpendicular bisector of WY. So we still have the same setup. This time WZ is 4n minus 3. And YZ is n plus 17. Find the length of YZ. This time we're going to have to do a little bit of algebra, but not too much because 4n minus 3 has to equal n plus 17. And we just do our couple steps of algebra. I get 3n equals 20. So n equals 20/3. So YZ equals 20/3 plus 17. 17, in order to add them, we have to have a common denominator. So 17 becomes 51/3, because 51 over 3 is 17. So that's 71/3 for my side. And again, we wouldn't express it as a decimal because it's not an exact decimal. We wouldn't express that as a mixed number because we don't use mixed numbers anymore. We're grown-ups now. Remember, equidistant, so grown up. Third one, when find Wx when Wz equals 20.5. So Wz is 20.5. I need to find Wx. This is what I'm looking for this time. Wy is 14.8. And YZ is 20.5. Now notice we weren't given that it's a perpendicular bisector this time. This time we were not told that it's a perpendicular bisector. This is the only information we're given. But because it is isosceles, because Z is equidistant from W and Y, it must be on the perpendicular bisector, which means this is a midpoint, dividing that equally into two spots. So 7.4 and 7.4. So Wx is 7.4. These are the types of problems you're going to see. You're going to apply our information. And we're going to look at this quite a bit. This is perpendicular bisectors. And by themselves, pretty easy to work with. What's going to make this chapter more challenging is the fact that we're going to deal with a lot more than just perpendicular bisectors. We're going to deal with angle bisectors. We're going to deal with medians. We're going to deal with altitudes. And each of them are going to have their own special properties and their special rules. And by themselves, pretty easy. When we start mixing it all up, there's a lot of stuff to keep track of. So my suggestion to you is to start keeping a little separate area of notes that talks about the special properties of each special segment we're going to deal with in this chapter. In fact, make yourself flashcards like we've done before. So you know, oh, it's a perpendicular bisector, and then list some properties of it. Any point on the perpendicular bisector is equidistant from the ends. And there'll be more properties to come. So really, take good notes with this stuff. Maybe make those flashcards. Start your first one today. The front would say perpendicular bisector. On the back, you got a couple facts right now to put on. You're going to add more. You're going to add more flashcards. And maybe by the end of the chapter, you'll have these things down so solidly that no matter how much we mix them up, you won't have any problem getting to it. All right, we'll see you in class.